This is the module 2, that is the week 2, and the lecture number 6, the first lecture. And basically in this module we will cover the heat and material balance, and in 3 lectures I will cover the heat and material balance. In the first lecture I will cover the overall heat and material balance in blast furnace, and I will show you with the help of a problem how to calculate the slag weight and the ore weight as well as the volume of the blast furnace gas based on overall heat and material balance, heat balance, that is the material balance. And the heat balance basically come into the subsequent lecture, heat and material balance, and we will basically talk in those lectures, that is your risk diagram. So, now in this we just simple overall heat and material balance. Before that, basically the concept that will be covered here is concept of heat and material balance. What do we mean by the heat and material balance? We have to understand that thing first. Second is that overall heat and material balance in a blast furnace with a problem, and if we do the overall material balance, not the heat balance, sorry, here basically I will basically talk about the material balance here in this lecture, okay, and with the problem. Now, concept of heat and material balance, what do we mean by the heat and material balance is that unit process, the unit process that we are considering, we considered as a black box, completely black box. We do not know inside what is happening, only we are concerned with the inputs and the output of the input flow and the output flow, and it is a steady state heat and material balance. That is very important. Thing is that anything unsteady we cannot consider here, because we are dealing with only the input and the output, and finally will equate the input is equal to output. Basically what happens, input is equal to output under steady state only, but because if you do some material balance, the material balance statement is input minus output is equal to accumulation. Input minus output is equal to accumulation, okay. So, that is a general statement without any source sensing. Basically, if something is generating and all this thing inside, that is there. So, input minus output is equal to accumulation, it is basically a transient state. So, accumulation becomes 0, that is when the accumulation is 0, then input become equal to the output, that is under steady state. So, we basically deal with that state only, that is where input is equal to output, right. Input is equal to output. That is the material and heat balance, macroscopic heat and material balance that I am going to discuss here. It is basically input is equal to output, and you have don't access inside the box what is happening. So, we are dealing with the input and output, and we can equate input and output, and then we can predict on how much is this thing. So, it is a completely steady state phenomena. There is nothing, because for example, something is coming in and then something is accumulating inside, a part of it is going out, then you cannot equate input is equal to output, because something is accumulating inside because of transient nature of the process. Transient nature of the process we will not discuss, it is perfectly steady state heat and material balance. So, that you have to understand. And finally, there is the no happening inside the reactor is of concern here, no happening inside the reactor. Suppose the material can undergo, there is lot of heat exchange take place inside, heat in gas, solid, sometimes heat is going from the gas to the solid, solids to the gas, and then heat exchange direction can change, then different types of phase formation, internal or intermediate phases can form, and then so a lot of things can happen. All these things of not concern, no internal heat exchange and phase change is taken into this consideration. So, those things will not be considered. For example, if we just let us consider the blast furnace. In case of the blast furnace, we can also take the blast furnace as a black box. And what are the input? We have some inputs. So, let us consider a 290 degree thing, Fe2O3 is coming in, okay, and your carbon is coming in, your gas, blast furnace gas, that is basically CO, CO2, nitrogen, this is coming out, and you have hot metal that is coming out, say some 1800 K, and these are soft 298. Let us, for the simplicity, let us consider 298, and then your air blast, that is the 298, everything is coming in. So, let us consider this process. Now, it is the black box process. So, your Fe23 is coming at 298, carbon is coming, let us consider 298. Air is also, let us for the simplicity, let us consider it is also entering at 298. Hot metal is coming out at 1800 Kil, that is the high temperature, and the gas is coming out at 298, and gas constitute of CO, CO2, everything. Now, inside the blast furnace, lot of reactions are taking place, right? It is the Fe23. Finally, when you consider, but our concern is Fe2O3 is entering and iron is finally coming out. Fe2O3 to Fe, that is the thing it's coming out. But inside, Fe2O3 may undergo this change, that is the Fe2O3, then phase change Fe3O4, then it is going FeO, then to Fe, lot of things are there, and then this reduction, all this indirect reduction generate the CO2, and then CO2 plus carbon is twice CO. Lot of reaction is taking place in the, basically here some reaction CO is generating, and then as the CO is moving up, as it is reducing the iron oxide, it is CO2 is generated, and then CO2 reacting with the carbon forming the CO gas. So, lot of happenings are there. There is a CO-CO2 exchange is going on. Finally, certain amount of CO, CO2 is coming out. So, all this inside happening, I just ignored about that. What I am concerned is that my Fe2O3 is in, carbon is in, iron is out, okay, and the gas is out, gas is CO and CO2. So, if I want to make an heat balance also, let us consider in that heat balance, then what I will see basically, that is the what is the fraction of CO and CO2 is there inside in the exit gas. So, that much of oxidation has taken place. So, that much mole of carbon has undergone, there is the oxidation. So, C plus half O2 forming the CO, and then C plus O2 forming CO2. For this reaction, if I know the mole fraction, that is the volume fraction of CO and CO2, I know heat of reaction for forming the CO and CO2. So, I can know how much heat has been generated inside. So, that is the way we can generate the heat generation inside without considering anything. All these things inside, that is the carbon is burning at the 2 and then the carbon gasification reaction taking place inside the blast furnace. All these details we are not considering. We are considering finally how much CO and CO2 is coming out, how much volume fraction or the mole fraction, mole of CO and CO2 is there. I know their heat of reaction, just I can know this is the supply of heat. And what is the heat requirement? Then I will see there is the Fe2O3. I will just consider Fe2O3 to Fe, decomposition of Fe2O3 to Fe, and then Fe to Fe liquid, that is the sensible and the latent heat, whatever you have to give. So, this is the heat demand, a very simple point of view I am telling. This will be the heat demand, and that is the heat supply. Heat supply is simply, that is the NCO plus delta H of F CO, and then plus NCO2 delta H of F CO2. So, minus of this thing basically you can take, because these are, it is the formation, this is. So, that will give you the heat generated, that is the heat supplied, and this is the heat demand. So, we are not going inside the furnace, what is happening there. So, we are basically concerned what are the inputs and outputs. So, from there I have to calculate what is the supply, heat supply, and what is the heat demand, and then just equate it, there is the heat balance is done. So, that way. Similarly, the mass balance if you do, I will see how much total iron is coming in and how much iron is going out, that is the way. Okay. So, any like Fe2O3 to Fe, the internal change Fe3O4, FU state change and all these things, we do not bother about that thing. So, that thing, there is no internal exchange or the phase change taken into consideration. So, I think this is simply clear. So, now let us consider a problem, that is the, let us read the problem and understand the problem and then do the material balance. There is a blast furnace makes pig iron, there is the blast furnace, that is the product composition is given, pig iron composition is given, there is 4% carbon, 0.5% silicon, 0.1% phosphorus, 0.02% sulfur, rest is iron, and ore composition is also given, and ore is 90% Fe2O3, it is quite good kind of ore. 90% Fe2O3 means your total iron is 63% total iron, because 70% Fe2O3 contains 70% of iron, 30% oxygen. From stoichiometry of Fe2O3 you can simply see. So, anyway, it is a good ore, and it has 90% Fe2O3 and 5% SiO2, 3% Ag2O3, 2% P2O5. Okay. The coke rate is given. This is 600 kg per ton of iron produced, and coke contains 90% carbon. So, and rest is silica and sulfur. Okay. The flux is pure calcium carbonate, and it is charged at a rate of 400 kg per ton of pig iron. Blast furnace exit gas composition is given. It says that 23% CO, 17% CO2, rest is nitrogen. Now, we have to calculate the weight of iron ore, volume of the blast furnace gas produced, and the weight of the slag. So, these are the things. So, it will be a simple overall material balance only. This is the material balance problem. Okay. So, let us see how we will attack this problem. First, we have to calculate the weight of the iron ore. It is very simple. If I want to calculate the weight of the iron ore, what I have to do? Yeah, I can simply do the iron balance, right? There is the elemental, there is iron balance. If I do, then I can get the weight of the. So, basically iron balance we do, there is the what are the source of iron? There is only one source of iron, that is the iron ore, because whatever the input you have to check. What are the inputs? Iron ore is an input, flux is an input, coke is an input, air blast is an input, out of which only the iron ore contains the iron. So, only source of iron is iron ore. So, iron coming from the iron ore, there is the Fe ore is equal to your Fe in the hot metal, because in the sink also, what are the outgoing gas in the blast furnace? If you see what are the input and output, and input and output, if you see, as I said, there is the ore is there, and then the carbon is there, you have a gas, right, you have hot metal, you have air. So, these are the things. So, out of which your ore is the, and then you can see from the outgoing, this is the gas and the hot metal and slag also. These are the output from a blast furnace, and hot metal only contain the iron, and in the blast furnace slag does not contain iron, because it is a highly reducing atmosphere. It is unlikely that if you will be there into the slag. In fact, slag is devoid of any kind of FeO. The blast furnace slag you cannot find any trace of iron oxide, because it is highly reducing, it is not there. So, it is you can assume that is the iron is only passing through the hot metal. So, whatever the iron coming in by ore, all the iron going through the hot metal. So, that is the simple iron balance. So, if you see the iron balance, if you know the ore of the, so for example, now you can easily calculate what is the iron through the ore, because say x kg of iron ore you require, out of x kg 90% is Fe2O3. So, you can say that is the Fe2O3 is 90 by 100. And in Fe2O3, this is the amount of Fe2O3, and Fe2O3 contain how much of iron? So, Fe2O3 112 gram of iron is there out of 160 gram of Fe2O3, right. So, because you can see Fe2O3, 2 Fe, 3 FeO. So, this thing. So, this is the total iron that is coming through the ore, that should be equal to iron in hot metal. Iron in hot metal, then you have to see 100 minus what are the other constituents are there, that is the 4% carbon and whatever else is there. That is the summation, you have to do the summation of elements, right, summation of elements, elements in hot metal, So, if you do that, so this into basically 1000 by 100, okay. So, that will give you the equation. So, simply this is the thing you have to do, and then let us do that thing what you are getting from here. So, x kg iron ore required, then you have this simple equation is there, that is you can understand that here this equation is simply you can understand that is x into 90, and there is 95.38, because all the impurities that is given there, if you add up 100 minus this, it comes around 95.38% is iron is there. So, in ton of iron, 1 ton of iron you have this much of ton of pig iron, you have this much of iron. So, from there you can simply calculate what is the weight of the iron ore, X is calculated, it is very simple, you can do that. Next is volume of the glass, there is a blast furnace gas produced. Now, if you want to calculate the volume of the blast furnace gas produced, how you can do that? There are two ways. One thing is that if you can do the nitrogen balance, you can get it, because whatever the nitrogen come through the air, same amount of nitrogen is coming out through the exit gas, because there is no sink for nitrogen, or that sink is not there. So, only coming through the air and going through the exit gas. So, you can do the nitrogen balance, but thing is that we do not have any information about the air blast and all these things. So, but another way we can calculate is if I know that is the moles of CO, CO2 produced into the exit gas. That is possible, because you see whatever the carbon is coming in, part of the carbon is going to the hot metal and rest of the carbon joining the exit gas. So, this carbon, whatever the carbon going into the exit gas, it contributes to all the carbonaceous component like CO and CO2. So, from there you can have an idea about the what is the moles of CO and CO2 will form if you just make a carbon balance, and that scope is here. Basically, we know how much the coke is coming in and all these things. So, we can make a carbon balance here. It is better because the data that is given, that way if you do a carbon balance, we can know how much mole of CO and CO2 is there in the exit gas, and we can do that. So, let us do a carbon balance. Carbon balance if I want to do, then what are there? There is the carbon is coming through the coke. A part of the carbon also come through the flux. Flux means there is the calcium carbonate. So, it also gives some amount of source of carbon, and coke is there. There is no other source of carbon, and carbon is living either through the hot metal, and rest of the carbon, majority of the carbon goes through the gas. Hot metal has some 4% carbon, right. So, if we can make this balance, then I can know how much carbon is living through the gas. So, how much moles of carbon living through the gas, and since I know the volume percentage of CO in a CO-CO2 mixture, then I can know how the carbon will be partitioned between CO and CO2. Okay, and then I can know how much moles of CO and CO2 will be produced. So, that is the thing I am going to do. So, next is that is this carbon balance. So, what is the coke carbon? Your coke rate is 600 and coke contain 90% carbon. So, that way this is the carbon that is coming through the coke, and then carbon coming through the limestone is simple like this, because in the limestone out of 100 you have 12 kg of carbon, because and you are charging at a rate of 400 kg per ton hot metal. So, this is the total amount of carbon that is coming in through the flux, and then the carbon in the hot metal 4% is there, simply 40 kg will be going into the hot metal and rest in the gas. So, C gas you find at 548 kg. So, 548 kg of carbon that will leave through the exit gas, and that corresponds to 45.66 moles of carbon. So, exit gas carbon, how much moles of carbon is going there, you know. Now, you can know out of this moles of carbon how much will be there in the CO and how much there will be in the CO2. We can simply, because I know the volume percentage of CO and CO2 in the exit gas. So, that is the CO moles, because I know 23% is the CO, and 40 is basically the total volume, that is the volume percentage of carbonaceous component, that is the CO and CO2. So, out of 40 CO and CO2, 23 is CO. So, this is basically the mole fraction of CO in the CO-CO2 mixture. This is the mole fraction of CO in the CO-CO2 mixture multiplied by this, that will give you the moles of CO into the CO-CO2 mixture in the exit gas. So, it is coming around 26.25. So, the exit gas volume you can simply calculate, because since you know the moles of CO, so 100 by 23, that is the total moles of the exit gas multiplied by 22.4 normal meter cube, that will give you 2557. That is this much of normal meter cube gas will be forming. Okay, because 23 by volume, it is present in the CO is present into the exit gas. So, from here the exit gas volume easily calculated. We can simply calculate by this rule. So, this is basically total kg mole of gas, and kg mole multiplied by 22.4, that will give you the normal meter cube, right. This, you just remember that it is the kg mole, okay, and it is basically I know 22.4 liter, that is the liter per gram mole. So, 22.4 normal meter cube per kg mole. So, this is kg mole, that is why it gives you the normal meter cube, right. So, this thing. Now, the slag weight, if I want to calculate the slag weight, I will do it by overall material balance, slag weight. Overall balance means I will just see two ways you can calculate it. One thing is the slag weight you want to calculate, then you can know how much of different constituents are there. Slag constituents, what will be the slag constituents? If you go back, you know, then it will contain CO, you can contain SiO2, because those are coming through the gangue. This gangue material partially is partition, but for example, silica is partition between the hot metal as well as slag. So I know how much silicon is there in the hot metal, so rest will join the slag. So that way I can, if I make a silicon balance, I can know how much of silica will join the slag. Similarly, if I make a phosphorus balance, because I know the composition of phosphorus in the hot metal and know how much phosphorus is coming through the ore. So then I can easily, by phosphorus balance if I do, I can know how much phosphorus will join the slag, right, as P2O5. Similarly, silica, phosphorus will be there, CO will be there, CO will be there, because it is coming from limestone. That is from the limestone, the CO directly join the slag only. There is no other escape, because all the, so if I make an calcium oxide balance, then also I know how much calcium oxide will come to the slag. So that we can do, but problem is then some amount of sulfur will also be there. But some data will be missing, because in the coke we have said 90% carbon, rest is silica and sulfur. So I do not know what is the partitioning between the silicon and sulfur there. So those will be difficult actually. So that way you can calculate it, but some data are missing there to calculate it. So otherwise you can do, that is one way you can do it, and other way is, that is the overall mass balance. If you can do the overall mass balance, then also you can calculate the slag weight, right. What is the overall mass balance? This is the thing, because I know the what is the total weight of the ore, right, and then I know the weight of the flux, I know the weight of the coke, and then I can easily calculate the weight of the air blast, because I know, now I know the moles of nitrogen in the exit gas. So since I know that moles has come through the air blast, so I can easily calculate how much moles of oxygen also come in through that air blast. So I can calculate the weight of the air blast. I know the weight of the hot metal. So I know the weight of the gas also, because in the gas all the mole constituents I know, that is the how much moles of CO is there, CO2 is there, moles of nitrogen is there. I just need the molecular weight of them and multiply, so I can get the weight of the gas. So I can do this way, and then rest will be the weight of the slag only. So this is also a way, and all the data are available that we can do. For example, the gas weight, if I want to calculate weight of the CO, then weight of the CO2 plus weight of the nitrogen. So how the weight of the CO can be calculated? That is the moles of CO multiplied with the molecular weight of CO, then moles of CO2 multiplied by the molecular weight of CO2, and then moles of nitrogen multiplied by molecular weight of nitrogen. Now, thing is, we know that moles of CO already we have calculated. Now, if I want to calculate the moles of CO2, NCO2, how do I calculate NCO2? Because I know there is the 17% is CO2 and 23% is 17% is CO2, out of 23 is CO. So NCO, if you just multiply it, then I can get, because this is the volume ratio, this is the mole ratio also. So I can simply get what is the moles of CO2. Similarly, I can get the moles of nitrogen also, that is 60 volume percent is nitrogen in the exit gas, and out of 23 is CO, and the NCO is known to you. So this is the moles of nitrogen, isn't it? So this way also we can calculate that, and if I do that, then it is done. That is your NCO2, that is NCO into 28, that is the molecular weight of CO, plus 17 by 23 into NCO. NCO, basically this is the moles of CO, that is this thing 17 by 23 into NCO, basically moles of CO2. This is basically your, this is the total is NCO2, sorry. And similarly, this value also, this is basically N of nitrogen, right. This is the moles of nitrogen, 60 by 23 into NCO, and this is the moles of CO2. So moles of CO2 multiplied by 44 molecular weight, and this is also multiplied by 28 is also molecular weight of nitrogen. So we will get to that. So, this thing, and then we can find that NCO, you can take it out common, and then you can find this thing, and then NCO you know, because this parameter you already calculated 26.45. So, multiplied you can find that 23533 kg. So, weight of the gas we calculate approximately 3533 kg, right. So, gas weight is also not bad actually. It is 3 ton of gas that is coming out. 3 ton of gas, not okay. Now, so now let us calculate, that is the weight of air blast. As I said, weight of air blast basically weight of nitrogen and weight of oxygen, and weight of nitrogen, then moles of nitrogen multiplied the molecular weight of nitrogen, and then moles of oxygen multiplied by the molecular weight of oxygen, and then NN2 into, now in oxygen NO2 basically we can calculate, this is basically your NO2 and number of moles of oxygen, right, is equal to 21 by 79 into NN2, because considering there is a normal here, that is 21 by volume percent nitrogen and 79 volume percent of oxygen, but for oxygen enriched blast or some other cases it will be little different, maybe different, but for normal air we can simply correlate, that is the NO2 is equal to 21 by 79 into NN2, right. Okay. So, then just, so NN2, there is the MN2 plus this thing, and then you just put the values, NCO, then now again MN2 also you can write in terms of NCO we have calculated 60 by 23, and then this thing, and then just put all the values, and it comes around 2519. So, around, that is your air blast volume, air blast was 2.5 tons of air blast was required here, okay, not bad amount. So, then you can just do the overall balance, that is the weight of the ore plus weight of the flux plus weight of the coke plus weight of the air blast is equal to weight of hot metal plus weight of slag and weight of gas, out of which we are unknown is only, this is the only unknown, and we can simply calculate it. We can simply calculate it by adding up this thing. So, weight of the ore we calculated 1514, and the flux rate was known to us 400, coke rate was known to us 600, and blast is this. So, actually we are not going into the intricacy of the coke, how much silica, how much sulfur, how much carbon. So, we are just taking the whole weight of the coke. So, this is one way good basically overall material balance, and then this is the weight of the blast, weight of the hot metal, slag, and the weight of the gas, and finally we can get, there is the slag rate is around 500 kg per ton of hot metal. It is quite little high. So, it is not a very good blast furnace basically nowadays. Slag rate, maybe slag rate varies from 200 to 400 kg, here it is coming around 500, it is little high. Okay. So, this is the way basically you can calculate the slag weight, and just by making an overall balance. And in industry you are required sometime always to calculate the material balance, and by material balance you can always calculate the slag weight, and it is absolutely, this balance is fine, and there should not be any chance of any error, and it should match with the experimental value, that is the, if you can calculate actually the slag weight. It is very difficult experimentally to calculate the slag weight, because of the slag metal interface there is always some intermixing, and exact value of the slag is difficult to get. Okay. But anyway, after that you can collect the slag, and then you can calculate it, but that will not may be very exact, and from here you can get a very exact value. Okay. Because there is no chance of any missing thing or anything. So, whatever is coming in has to come out. If we consider the blast furnace, obviously is a steady state process, and we can, blast furnace is a steady state process, that I have said earlier also, because after starting the blast furnace, after few days it comes to a steady state, because you are giving charging at a particular amount of material and you are taking out a particular material out. So, any continuous process after starting then it becomes a steady state, okay, because everything inside comes to a steady state operation. And sometimes it becomes unsteady state, because when you give suppose the air blast, you want to increase the productivity, you are giving some amount of air blast, increase the air blast, some transient situation goes on, and then again comes to a steady state thing. So, this is basically the problem that I am demonstrate here is basically from the class notes of Professor Ahindra Ghosh at IIT Kanpur, and that I have discussed here, that problem, and it was a very nice problem from that time. So, what we did basically here, we discussed the concept of overall heat and material balance in the blast furnace, and what we said is that the material balance is done in a continuous process in a steady state mode. Okay. When we do the material balance, we just make the input is equal to output, that means we are considering a steady state process. Okay. And anything happening inside the reactor we are not bothered about, we only analyze the input and output, and based on that we make an heat and material balance by equating input and output, and we can predict on that thing. So, it has to be a steady state process, and it shows the we have discussed one problem, and for a blast furnace. So, you given a ore composition, hot metal composition, and coke rate and the flux rate. So, you can calculate per ton of hot metal what will be the weight of the iron ore, what will be the slag weight, what will be the volume of the blast furnace gas, and all these things. So, I think this amply clears that is by overall material balance, how we can utilize it for a plant application also. In the plant it is very useful, actually in the plant you can calculate the slag weight very effectively. Thank you very much.